Part 1 covers converting DICOM sequences to a 3D image volume. For example, MRI Convert will extract a 3D volume from a series of DICOM slices on a CD. Let's start our image analysis by opening MRI Convert. Now click on Add Folder. You should have a disk with all of your patient's images from the PAC system in your computer. Browse for that folder, and the program will look for all of the images that it can convert. This process can take a long time if there are a lot of images on the CD. It's important to select the conversion type. In this example, we'll use Analyze 7.5. Select Convert All, and a folder will be made on your desktop with all of the file conversions. In Part 2, we assume that the 3D volumes have already been created. In this part, we will strip the brain away from the skull and use that to co-register the PET scan. Open the PET scan and the MRI scan in MRIcron. Notice that the two images are not co-registered because they were acquired in different orientations. The MRI still has the skull in the image. Open the MRI in BrainSuite. If it's hard to see the image, use the first slider in Display Properties to adjust the visibility. Select Skull Stripping from the Cortex menu. In this dialog, adjust the second and third parameters if you need to, and apply to strip the skull. If you need to go back, press back 4 times to readjust your parameters. View the entire volume. If you're satisfied, apply the Mask tool from the Tools menu to create a brain mask. Save the primary volume, which is the patient's brain without the skull. Then save the mask volume. We will use this again later for several purposes. Next, we cover co-registering the PET scan to the skull-stripped MRI. Studies may have been acquired in very different spatial orientations, sizes, and locations. They need to correspond to the T1 anatomical reference. Open BioImageSuite. You can hide the command window, but don't close the black box or all of BrainSuite will be closed. A registration menu opens, followed by 2 viewers, one for the anatomical reference MRI and one for the image we need to transform. It may be helpful to make your image directory the default using Switch Directory from one of the viewer's file menus. Load the PET image you need to transform in the Transform viewer. Load the skull-stripped reference T1 MRI in the Reference viewer. Change the mode in each viewer to 3-slice plus 3D. And change the volume type button to volume. This will show each image in 3D. Choose manual reslice controls from the Transform Viewer Image Processing menu. By convention in imaging programs, the blue line is vertical, Z-axis, front-back is green, Y-axis, and left-right is red, X-axis. Click the Manual Reslice button. Now the image orientations match. Changes will not be saved in the image unless you click Copy Results to Image. The reoriented image with a new descriptive name that indicates what's been done to the image. You may close the image processing controls. Now use the registration controls and registration menu to bring up the controls for linear registration. Then click Run Algorithm. You can ignore the Save Matrix dialog. The co-registration of the PET scan to the MRI. The cursor location in one viewer should match the cursor location in the other viewer's image. When satisfied, click Copy Results to Image and save the co-registered PET scan with a descriptive name. Open the co-registered PET and MRI in the MRI-Cron program. Double-check the registration here as well. The PET scan's draw menu to open VOI. Change the file type to Nifty or Analyze Header to allow you to use an image volume as a volume of interest. Then select the mask file you made in BrainSuite when the MRI was stripped. Use the draw menu to mask the image with the volume of interest and preserve the regions with the volume of interest. Close the VOI mask and save the masked PET scan with a descriptive name. The stripped MRI, the PET scan now shows only the cerebral portions of the volume. This is useful when you superimpose the two images. Merge the masked PET scan with the side-by-side MRI and move slowly through one axis to look for a region that is more hypometabolic. It can be very helpful to use a different color map like French to accentuate subtle differences. Drag with the right mouse button to turn everything else white but this region and make certain no other region is more hypometabolic. Now select the 3D Volume of Interest tool. Adjust the first two parameters in this dialog until the volume of interest is highlighted. It may be helpful to select Zero Intensity Constrains the Edge. When you're satisfied, click Apply to create the volume of interest. You can use the Draw menu to save the volume of interest with a descriptive name. can use the Overlay menu to see the volume of interest on the MRI, or the Draw menu to mask the MRI with the PET volume of interest. Open the co-registered PET scan in ImageJ. You can adjust the image intensity in the Image menu. The Edit menu to select all of the slices of the image. And use the Edit menu to invert the image. You want to invert all of the slices of the image. The inverted PET scan as an Analyze 7.5 file using a descriptive name. Compare the original PET to intensity inverted PET scan. In this case, that the image is flipped on the y-axis. It's still co-registered, but the orientation has changed. Open the T1 image in Amide as an anatomical reference. Always ignore the duration warning. Click on the T1 to make. Right-click on the T1 to adjust its properties. Change the color map to the first choice in the drop-down menu. Choose Import File, not Open Study to bring in your PET scan and inverted PET scan. Here you can see how the PET scan orientation is changed relative to the T1 reference image. Click on the PET scan to adjust its properties. Rotate tab to invert the axis, which restores the original orientation. Deselect the T1 image since you don't want to merge it with the PET scan. Use the File menu to export dataset. Select all visible datasets, Analyze, and Inclusive, then execute the save. Overwrite the old masked PET scan file. Follow the same steps for the inverted PET scan. Amide and verify the orientations of the T1, PET, and inverted PET scan. Windows, FSL must be run inside a Linux virtual machine called the VMware Player. VMware Player. Virtual machine. Log into Linux. The header and image files of the skull stripped T1 onto the Linux desktop. Start FSL and run fast segmentation. The header file of your skull stripped T1. Check partial volume maps, but be sure to check binary segmentation, one image per class. Then click Go. This is one process that actually takes quite a bit of time. You'll see the new images appear as compressed folders. Exit fast. The image we need is labeled T1 Seg1. This is the gray matter volume. Drag it into your working folder in Windows. You can close FSL. Trash all of the files you added to Linux. Power off and close the VMware Player. Check the results of your segmentation. Open the T1 image in MRIcron and add the segmentation as an overlay. In this example, we will use MeVisLab, or Medical Visualization Laboratory, to create from scratch a 3D visualization of the PET surface and volume of interest. In MeVisLab and use the module Quick Search to find a file loader. We will use the ITK image file reader. Give this module a descriptive name like T1. Double-click on the module and browse for your skull script T1 MRI. Close the Properties box with the red X, not the Close button, which unloads your image. We need a 3D viewing module like View 3D. Click View 3D to open the viewer. The triangles of both modules. The left mouse button to drag and rotate the image. Shift or cursor key to move the image around. The Shift and the cursor key to zoom the image. Sliders in the Clipping tab to clip into the image. Notice how the image is rescaling as you do this. The right mouse button to change the windowing and thresholding. You can prevent the rescaling by unchecking Auto View All. You may hide the orientation preview and annotations or background. Add another file reader for the PET scan, or just copy and paste the first file reader, then rename it PET. Click and browse for your PET file. You could connect this PET scan to the 3D viewer if you like, but we have other plans for it. Load a new module called IsoSurface to depict a surface rendering of the PET scan. The PET file reader to the IsoSurface module with the triangles, and then the half circles of the IsoSurface module and 3D module, and disconnect the triangles. Click on the IsoSurface module and change the ISO value to something smaller. Be sure to click Auto Update and Auto Apply. We need the SOWEM renderer to modify the color. Squares of IsoSurface and SOWEM renderer. This half circle to connect to View 3D. Now change the color of the IsoSurface. Let's choose blue for a hypometabolic feature like this. If the ISO value is enough, you'll see holes appear in the PET scan, representing the more hypometabolic regions of the study. The goal is to find an ISO value that shows the fewest holes. These are the most hypometabolic regions on the lateral surface. Fortunately, this method will not show the interior surfaces very well. And of course, missing regions are difficult to see because they're not there in the image. We need an alternative way of visualizing the hypometabolic cortex on the MRI. You may superimpose at the co-registered T1 and clip it, but you can't clip the IsoSurface. Copy and paste these three new modules to use with another image. Here we will rename the PET file reader as PET VOI. Click and load your PET VOI image. This as well to the 3D viewer. Change the color to red since this VOI is inverted in intensity and is also segmented to show only the cortical portions of the PET. Notice this region appear in the whole of the PET IsoSurface. Change the ISO value to show more or less of this hypometabolic cortex. You'll often find tiny rims of dura at the extreme surface. Change the resolution to see more detail, but it takes longer time to render this. T1 to viewed 3D. Disconnect the PET isosurface, the most hypometabolic cortex of the MRI. If MeVisLab sees the regions on the wrong side of the brain, you can make a quick viewing adjustment. Load 3 copies of ITK Flip Image Filter, insert them between the file reader and the viewer. In this case, we want to change Y from 0 to 180, flipping front and back and left and right at the same time. Of course, you want the same arrangement for all of the images. Flipping in various planes illustrates that this most hypometabolic region is in the left superior temporal gyrus. To save your new network. This can be used as a template when you start a new patient's study.